Welcome to the world of recurrent neural networks, also known as RNNs. In this presentation, we will explore how RNNs are used for sequential data processing. Get ready to understand the core concepts behind these powerful networks and their applications in various fields. Traditional neural networks often struggle with sequential data due to their inability to handle variable length inputs, capture temporal dependencies, maintain context across time steps, and process ordered information effectively. Recurrent neural networks, or RNNs, address these challenges by maintaining an internal state that acts as a memory of previous inputs. This allows RNNs to process sequences of data in a way that considers the order and dependencies between elements. Examples of sequential data include translating hello to hola, representing notes in music such as C, which leads to E, F, G, predicting time series data where T-2, T-1 predicts U plus 1, and understanding language where the cat leads to sleeping. A recurrent neural network, or RNN, maintains an internal state, also known as a hidden state, that is updated at each time step. This enables the network to capture temporal dependencies within sequential data. Let's look at a basic implementation of an RNN cell. The function RNN_cell takes an input x_t, the previous hidden state h_previous, and weight matrices w, u, and v. First, we combine the input and the previous hidden state to compute the current hidden state h_t using the hyperbolic tangent activation function. Then we generate the output y_t by applying the weight matrix v to h_t. Finally, the function returns the updated hidden state h_t and the output y_t. Here are the mathematical formulas that define the forward pass in a recurrent neural network, or RNN. The hidden state at time step t, denoted as h_t, is calculated using the formula h_t equals hyperbolic tangent of open parenthesis w_x h times x_t plus w_h times h_t minus 1 plus b_h close parenthesis. The output at time step t, denoted as y_t, is calculated as y_t equals w_hy times h_t plus b_y. The hyperbolic tangent activation function is defined as hyperbolic tangent of z equals fraction e to the power of z minus e to the power of minus z over e to the power of z plus e to the power of minus z. In these equations, x_t represents the input at time step t, h_t is the hidden state at time step t, w_xh, w_hh, and w_hy are the weight matrices, and b_h and b_y are the bias vectors. The hyperbolic tangent, or tan, is the hyperbolic tangent activation function that introduces nonlinearity into the network. Recurrent neural networks, or RNNs, can be structured in various ways to handle different types of sequence-related tasks. These structures are referred to as architectures. The four main types of RNN architectures are as follows: one-to-one, in which a standard neural network processes a single input to produce a single output. One-to-many, in which a single input produces a sequence of outputs such as in image captioning. Many-to-one, in which a sequence of inputs produces a single output, such as in sentiment analysis. And many-to-many, in which a sequence of inputs produces a sequence of outputs, such as in machine translation. Recurrent neural networks, or RNNs, have a wide array of applications across various domains. In natural language processing, they can be used for text generation, machine translation, and sentiment analysis, as seen in applications like Google Translate and ChatGPT. In speech and audio processing, RNNs enable speech recognition, music generation, and audio synthesis, exemplified by voice recognition systems like Siri and Alexa. For time series analysis, RNNs are employed in stock price prediction, weather forecasting, and sensor data analysis, often used in financial forecasting systems. In video processing, RNNs contribute to action recognition, video captioning, and motion prediction, which are used in security surveillance systems. RNNs also play a role in bioinformatics, aiding in protein structure prediction and gene sequence analysis, as seen in DNA sequence analysis tools. Lastly, they are used in behavior analysis for user behavior prediction and anomaly detection, powering recommendation systems. Long short-term memory networks, or LSTMs, are a specialized type of recurrent neural network designed to mitigate the vanishing gradient problem through the use of gating mechanisms. Key components of an LSTM cell include a forget gate, which decides what information to discard, an input gate, which decides which values to update, an output gate, which controls the output flow, and a cell state, which acts as long-term memory storage. Here is an example of a basic LSTM cell forward pass. The function LSTM_cell takes an input x_t, the previous hidden state h_previous, and the previous cell state c_previous. The gates f_t, i_t, and o_t are computed using the sigmoid function. Finally, the cell state is updated. The gated recurrent unit, or GRU, is a simplified version of the long short-term memory network, or LSTM. It combines the forget and input gates into a single update gate and merges the cell state with the hidden state, resulting in a more streamlined architecture. Key components of the gated recurrent unit include the update gate Z, which controls information flow, the reset gate R, which determines how to combine new input with previous memory, and the current memory content H tilde, which represents the candidate activation. Here are the update equations. Z subscript T equals sigma of W subscript Z times the concatenation of H subscript T minus 1 and X subscript T. R subscript T equals sigma of W subscript R times the concatenation of H subscript T minus 1 and X subscript T. H tilde subscript T equals hyperbolic tangent of W times the concatenation of R subscript T element Y's product H subscript T minus 1 and X subscript T. H subscript T equals 1 minus Z subscript T element Y's product H subscript T minus 1 plus Z subscript T element Y's product H tilde subscript T. Compared to LSTMs, GRUs have 2 gates, update and reset, while LSTMs have 3 gates, input, forget, and output. GRUs use a single state, while LSTMs use a cell state and a hidden state. GRUs have fewer parameters, leading to faster training, while LSTMs have more parameters, making them more expressive. When training recurrent neural networks, or RNNs, several challenges can arise that affect the model's performance and convergence. One significant challenge is the vanishing gradients problem, where gradients become extremely small when backpropagating through many time steps. This can be addressed using LSTM or GRU architectures, gradient clipping, and skip connections. Another challenge is memory constraints, where the model has limited ability to retain information over very long sequences. This can be mitigated using attention mechanisms and truncated backpropagation through time. Gradient clipping is a technique used to prevent gradients from becoming too large during training, which can lead to instability and poor convergence. The train step function takes the model, optimizer, and a clip value as inputs. It computes the loss, calculates the gradients, clips the gradients by the norm, and applies the clipped gradients to the model's weights. Here are the key takeaways from this presentation. Recurrent neural networks, or RNNs, process sequential data by maintaining state information. Long short-term memory networks, or LSTMs, and gated recurrent units, or GRUs, address the vanishing gradient problem. Different architectures are suitable for different sequence tasks. For best practices, choose an appropriate architecture for sequence length, apply gradient clipping during training, and consider bidirectional variance for context. Common applications include natural language processing, time series prediction, speech recognition, and music generation. Future trends include integration with attention mechanisms, hybrid architectures with transformers, and efficient training on longer sequences. Some resources for further learning include deep learning frameworks, research papers, and online courses. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.